Good morning, good afternoon, good evening, everybody. Thank you for joining in. My name is Bhumi Gadia. I'm your host for today, and today's presenter is going to be Matt Coakley, who is a product manager for Marc and all of our nonlinear solutions. And as many of you may know, we released Marc 2020 last week, and we're really excited to show everything new that we have added in this version to everyone on the call today. Keep in mind that this webinar is being recorded, and we will post a recording of it on our YouTube channel. You will also get an email notification with a YouTube link later today or tomorrow, so stay tuned for that. If you have any questions during the webinar itself, you can ask in the Q&A panel, and either me or one of the panelists can answer those questions during the presentation. If it is something that needs to be discussed at the end, we will read it out loud and then answer it at the end. If you're facing any technical difficulties, please type them in the Q&A in the chat panel, and I can try and help you out from here. Just stay tuned, and if nothing works out, then we'll send you the YouTube link as well. With this, I will I'll change Matt as the presenter, and he will get started today.
Thank you, Bhumi. Welcome to the webinar. We're going to talk about what's new in Marc 2020. I want to take a second to thank Audrey Bout, our development manager, and Yashwant Talani, who does our QA. The team's really pulled together in a difficult time, and we have a really great release. Thanks also to all of MSC that supports us with packaging, documentation, etc. The beta testers as well, both public and internal. You'll see that we have some really great functionality that they've been able to run through the courses. So I'll go ahead and get started and show the Marc 2020 contents. We'll talk briefly about what we're going to talk about in more detail in just a minute. We'll start off with some of the new and expanded workflows. One of these, the first one's actually going to probably come as a bit of a surprise to some people who may have looked at the beta webinar, though I did tease it. We'll cover an elastomer fatigue life calculation that we have put into Marc. I wanted to especially thank Andy Bell from our application engineer team who really worked hard to beta test this. It's a good capability, and I'm excited to show it to you. We also have some exciting things in creep material data fitting, induction heating improvements, and I'll talk a little bit about co-simulation compatibility. From Smarter Solve, so this is something I've been talking about now for multiple releases. We're focused on making the solver more adaptable, more flexible, open, and generally a higher performing solver, interactive as well, but a higher performing solver. And we are trying to make it smarter so that it's easier on you. I think in the situation we see that especially the adaptivity, the solver recognizing things to be increasingly important as we're trying to all ramp back up. And I think you'll see some things in this release in that way, primarily around contact. Contact is something we've been working on. We already have excellent contact capabilities, and we continue to improve them to ensure that we stay best in class. We have some iterative solver GPU support and analysis statistics reporting. And then what I started calling the smarter simulation environment, primarily around Mentat and our GUI. Right now, we've added model dimension. I'll explain that in more detail. And then we have a large bucket of ease of use enhancements. I'm actually excited to talk about these very much because we find that these are issues that people face every day. So that's the contents of what I'm going to talk about. For more details and additional information, you can look at the documentation included with the release. So I'll go ahead and start with the new and expanded workflows. And the first one of these is this elastomer fatigue life calculation. So Prior to this release, Marc built-in capabilities for modeling the damage in rubber were really associated with the Mullins effect. So the Mullins effect, as you cycle a elastomer or a rubber material, you'll see a degradation until you reach a stabilized cycle. We've had Mehe for some time. We've introduced Ogden-Roxburgh fairly recently. But we've also seen a large number of requests for fatigue damage modeling. And so in response, we decided to start working on that, and we've developed an initial elastomer fatigue capability. The implementation requires light curves for uniaxial tension or torsion. You enter them as a table, or you can represent them via a Wohler curve. This power law you can see here that my pointer is on, where you need to fit the A and the N parameters to the test. The simulation uses the maximum principal Green-Lagrange strain or the maximum principal logarithmic strain. You have your choice there. If you, in your own methods, use a different strain and you'd like us to incorporate that, please let us know. But this is what we find is most prevalent in the literature today. It supports constant amplitude, block, and rainfall counting of an actual load history. So obviously, constant amplitude is pretty straightforward, as is block. The rainfall counting is very cool because what you can do is you can actually give it a complicated load history, a simulation of that, and it will identify your major peaks and valleys, and then you do not have to do that. It will do that for you. The other thing that was very important with elastomers was that it's fully compatible with adaptive remeshing. So all the fatigue results are mapped to the original mesh. Obviously, when we're dealing with rubbers and elastomers, it's not uncommon that adaptive remeshing is used. And so it was important to us to make sure that we had that supported. There's also additional advantage when you have remeshing, besides the fact that you can use it, is that when we remap back to the original mesh, when you go and if you have to modify your mesh, you know exactly which nodal points in the original configuration or which element some of your hotspots were around. The damage accumulation for the variable amplitude and the block loading is really done via the Palmgren-Minor rule, as shown below here. It is really a fraction of the fatigue life based on the number of cycles that were actually exhibited versus the number of cycles of failure. A fairly straightforward method for determining the damage accumulation. The actual implementation, there are some new menus, but there's actually some important things as we talk through. When you have a hyperelastic material, you'll now have a fatigue button. And when you click on that fatigue button, it opens up another menu. Depends on whether you're doing the power law or prescribing tables, picking the damage parameter in terms of the strain, and then your A and N parameters that you have defined. That's all that's required from the material point of view. When you go to the job definition, we now have this fatigue analysis in the job properties menu. There's something here, though, I want to point out that's actually quite important for two reasons. One, if you don't see it, it's because you haven't assigned a material fatigue properties. This is an interesting and actually a very smart way of starting to add things, and something we can consider elsewhere is that since it's context sensitive, it's aware of whether or not you define fatigue properties. It won't show up until then. Why this is important is it really helps with menu clutter, right? Some people like to have the whole menu there, but it can be quite distracting as we add more and more options. And so this was a very smart way of implementing it in the GUI such that it's context sensitive. And it's something that I'd like to have feedback on because I'd like to see more of it. When we look at the job properties, You can also see that this is not the normal job properties. And here's another case where when you're doing fatigue analysis, a lot of the other aspects of it don't apply. So, so if it's not applicable, it's not shown. And this is, again, another way of us simplifying the GUI while enabling you to do the work that you need to do with fatigue analysis in this case. So again, this is another smart implementation of the capability that you do not have the full menu when it doesn't apply to a fatigue analysis run. So once you define this fatigue job, the only remaining aspect is you can see this middle area. I expanded up here into the different types of loading. You define your loading. So this is not your typical load case. This is where you've actually run your simulation before and deciding whether you're going to do a constant amplitude load and pointing to the increment number, whether you're going to do block loading or reporting to different jobs and different increment numbers and how many cycles happen, and then to the most complicated where you're doing a variable amplitude load where Marc will figure out the rainfall counting for you. And at that point, you would just press run, except you must remember you definitely want your fatigue output. As I mentioned before, the user must request your principal values of logarithmic strain in order to calculate the two values, or one of the two values, depending on which you requested for the criteria. And then we have new output, number of cycles to failure with a log10 version as well, a fatigue damage, that Palmgren minor rule I talked about, and then the fatigue life. Both the cycles to failure and fatigue life have a log10. Very important when you're dealing with fatigue as well, since the range is so large in terms of fatigue life in a typical specimen. Some examples. We did on the top, you can see just a typical test specimen. We modeled axisymmetric. Here is the fatigue life calculation that we did, and it is in the linear scale. And as you can see from here, it's it would lead you astray just if you were going by the colors. It's when you look at the log10, in which case you can really see the differences in fatigue life. We've implemented something else as well that is applicable definitely for fatigue, but could be applicable elsewhere. We've had similar requests for this, and that is to reverse the legend to essentially make the low values colors that primarily you associate with the low values now associate with the high values and vice versa, as fatigue is one of those cases where the lower the life, the worse the case, and so generally people like to see that in the red. So we now have this legend reversed option, and you can use that for fatigue or other things. So that's a nice little addition that came with this. If we look at a 3D case we did with half symmetry, we also kind of showed the fatigue life here as well. So this was maybe a surprise to some of the beta testers. As I said before, I did tease that we were going to work really hard to get this in, and we were able to get it in. A lot of hard work and an impressive display of from the product development, the QA testing, and the beta to get it in. So we're quite proud of this, and please let us know what you think of it. This is only the beginning of this fatigue life idea in Marc. Creep simulation. So whereas the previous one was a brand new type of workflow we implemented, creep has been in Marc for some time. But when you look at the equation, for instance, for the Maxwell creep, and you start breaking it down, there are a lot of different parameters, material constants that have to be obtained, generally obtained through testing and comparison with experimental tests. So it requires a fair amount of effort from the end user, manual fitting. Manual fitting, anytime you introduce the word manual, you always run the chance of an error as well, accidentally. So when we see this kind of behavior, particularly with materials, what comes to our mind, of course, then is experimental data fitting. So we can now fit the creep experimental data fitting. You have to prepare a ragged table of the experimental data and the independent variable types. But then at that point, you can go into the experimental data fit, select creep, add the data you want, specify the law you want for the stress dependence, and then execute it, and you can get the coefficients that you need to get to set up the behavior. So experimental data fitting, if you remember, is something I think we've had a project on it for many, many releases. I think it's quite a useful capability for our end users. In this case, it really opens up, I think, creep to more users, and for those ones who are doing it, it should make it much more easier to work with. Just an example, on the left here, we did the experimental data fit with an aluminum at a single stress level but multiple temperatures. And over here on the right was the comparison of the data fit with aluminum at a single temperature but multiple stress levels. And so we like the agreement that's happening there. And as always, please provide any feedback, which is a broken record for me because I say that on almost every one of our enhancements. The feedback is critical. Note that many of these are coming from requests. This was a request as well. Electromagnetic simulation and manufacturing. So a lot of our electromagnetics is around heating using induction coils. We continue to refine this application, and we're really getting to an incredibly good capability right now, very well-rounded, very accurate. So in early releases for 3D, we required a body of revolution to be used for the coil shape. That's no longer necessary. Now we can do any arbitrary shape that you have modeled in 3D. We can use that for the coil. And then the other thing we did, which is kind of a lead-in to the Smarter Solve, is we've looked at the efficiency and speed and performance of doing this kind of calculation for the current. And we found that it was time-intensive enough with 3D models and nonlinear behavior that we needed to improve it. So we reformulated the calculation, and I'll show you some improvements in a minute. This is an example here of a coil. It's not quite the pancake coil that you saw on the other slide, that maybe you have something like that even in your induction stovetop at home. But you can see this coil shape. It is definitely not a revolution in the sense it's spiraling outward. And so the menu is actually quite simple. The procedure is quite simple. You just have to define your terminal nodes, your begin and your end, and mesh up your solid, and you have your coil shape however you would like it to look. The new, more efficient calculation of the induction current is the new default. So you don't have to set anything to get the better performance that we're going to show. The 3D example of the coil, you can see here, where we just heat up a plate, and we've got the pattern that you would expect. We're pretty happy with this. So if you're doing this type of application, please provide us the feedback there. But we are quite satisfied with what we have so far. And when we look at the performance improvement, I'm showing axisymmetric. Obviously, I could not show this kind of coil performance improvement because we couldn't do it in a previous release. But this is something we could easily do in previous releases. And Marc 2019 FT1, it took 401 cycles. And Marc 2020, the new release, it took 120 cycles. So we dramatically improved the efficiency of it, and we reduced it by 70%. That doesn't necessarily directly translate into 70% wall time, because there are other things that take time, but it's quite an improvement in the targeted area we wanted for induction heating. So co-simulation, I'm not going to talk too much, except that it's incredibly cool to see. You can see this baffle valve, you can see with the CFD and Marc simulating the behavior of the valve. We can couple today structural mechanics, multi-body dynamics, computational fluid dynamics. Previous releases, it was limited to coupling 2 simulations, and cutbacks were limited to 1 application. So when the CoSim is released, the Marc team needs to stay compatible and make sure that our product is working well with that. And for this most recent release for CoSim, they introduced 3-way coupling, and there's cutbacks are done arguably in a way which is the correct way, which is that if one of the codes involved has to cut back, then all of the codes go back and resolve at that time level. It of course results in a little more time, but it is incredibly more accurate because you're not making assumptions about linear interpolation. And of course, if it's co-simulation, you should always be running all solvers at the same time step. So hopefully this plays. Yes, it is. Here's an example with Marc with this big storage tank, and then the fluid inside you can see sloshing around during an earthquake. So this is just some of that capability you can have. We would love to have all of this natively within Marc, but it would be a significant effort, which we wouldn't be able to deliver any of the other capabilities we're talking about. So co-simulation, I think, is a very important way for us to move forward, and it's an interesting way to look at Marc and how it fits into a larger ecosystem. I'll now talk about the smarter solve improvements. Again, to reiterate what I said earlier, these are the ones that we really feel apply to the vast majority of users in some way or another. They're really about making your daily use with the code better, independent of what workflow you might be working on. So I'll start off with the contact ones. Segment-to-segment stress-free initial contact. So it's not uncommon that your geometry or meshing results in small unintended gaps. This one here is a little bit artificial, but it's still possible, maybe where the CAD came in or your CAD person wasn't paying perfect attention, is not perfectly lined up, you have small gaps. Maybe there was even a small shim here that you didn't want to address. There are some ways of dealing with this, or other ways, but one way that a lot of people like to do is just do this stress-free initial contact adjustment, which then closes those gaps. It's not new to segment. We had a previous algorithm that we used. The problem is that it didn't allow the user to observe the magnitude and location of the adjustment, and the adjustment was lost when you subjected it to large-scale sliding. This was not an issue with node to segment, and still is not an issue with node to segment. It was only segment to segment that illustrated this problem because of the initial way we set it up. So we revisited this, and now the new stress-free initial contact is similar capability as what you have in node to segment, where you can actually visualize the adjustments and they're retained during large-scale sliding. So you can see here, imagine you want a perfectly neat fit pin, but in reality, you have gaps in here, maybe just because of discretization or other aspects. And so you can do the stress-free projection. That's shown here by the arrows and how much it had to adjust each node. This is the new default, this new formulation, so you don't have to do anything to get it. And it is behaving much better and equivalent to node to segment. So we added a linear contact formulation. I always have mixed feelings about adding linear-based behaviors to our nonlinear product, but there is no doubt that in certain cases, the whole analysis is not necessarily behaving nonlinear, and if we can put a linear capability in there, as long as the user checks it against the assumptions made, it can really speed up an analysis. So Nastran has a linear contact capability, and we took a look at it and said, hey, this could be useful within Marc as well and save some time. The important part really is the assumptions that are made. Your contact throughout the simulation has to be described by the initial configuration, so you're not having new nodes or patches coming into contact. And the sliding has to be small, so it doesn't result in nodes or patches changing the segment they contact. So in some cases, this is just is not going to be in your analysis, but when it does, we have this capability. It's not the same as glued from that capacity. It is more like contact. Common scenarios might be maybe you have some aerospace applications where you have small strain inertia relief, contact with infinitesimal displacement rotations, for instance, maybe an engine block analysis. I think that preloaded bolted joints, where you're subjected to primary shear loading, the bolts take the majority of the, or they do take the shear, unless you would actually have some friction as well. And so these are areas where you can maybe benefit from this linear contact formulation. It is certainly not the default. The default is always a nonlinear in the product, but you do have an option now here under contact control to switch it to linear depending whether you're node to segment or segment to segment. So here's an example of a problem we ran where you got two flanges bolted together. We got similar results with the linear contact. We saved 16% in the time. Unfortunately, I can't show you another example of another extreme. This was a confidential model, but if you just envision large stacks of plates together, bolted together, the wall time reduction was about 80%, and you got similar results. So you can see that in the right cases, this actually adds quite a bit of efficiency to the solution. Again, it's a really great capability, but again, I just stress, please make sure your assumptions are valid when you do that. It's also not a bad idea if you're running an initial analysis to even turn it on initially and then switch it to nonlinear if you really want to check it at the end. As part of the Smarter Solve, right, is about looking for inefficiencies, looking on how we do things, and we looked at node to segment in some recent problems that we were helping with in the development team, and there's issues with solution convergence. Right now, the process that we go through when we are checking for contact is we make sure our convergence criteria is set, right? So we would go all the way down, and then we would check for the separation, and then it would reset the count, iteration count to 1, and iterate again with the new contact conditions. This works. The problem being is that maybe earlier at a relatively small amount of error, we actually saw the actual separation changes, and there's a good chance that iteration 5, 6, and 7 were just iterating on a condition we were going to show was not actually going to be valid anymore because the separation changed earlier. So in doing this, we implemented a new accelerated check, right? And this forces Marc to check for separation when the maximum residual force is less than 10% of the maximum reaction force. There's nothing magical about 10% yet, other than the fact that it seems to work well for us. It seems to be engineering sense to be a good value. That might through feedback change, but it's definitely worked well for us in our testing. And when we see that is done, we will then do a check for the contact condition changes. And if we do see it, then we will start the iteration over again, and we will start with a new contact condition. So we eliminate those iterations that might be associated with a contact condition change that's getting close to the error that we see. This is not a default behavior. This one we felt was a big enough change that we did not want to turn it on by default yet. So you have now under your check for separation, you have a default, and then you have this accelerated that you can choose to turn on, which results in the earlier check for contact separation. We do see a significant savings in this example. There was 137 iterations before, and there were 83 iterations after. That's about a 40% reduction. And, you know, anytime we're reducing iterations, that is directly associated with a pretty good reduction in the runtime. Not exactly the same one for one, but tends to be quite similar. And then we get a little more in the nuts and bolts, just making you aware. We did look at the contact nodal projection as well, and we did see that there are some things we could do to improve that. So we ran some we made some changes, we ran some models. We're getting similar results, but we're getting a better time reduction. You don't have to do anything for this. This is just on by default. So even running the same problem in a prior version and this version, you should see a potential reduction in your time. GPU and performance. So maybe, I guess it was probably 10, 15 years ago, GPUs started really coming on the scene for CAE applications, and there was a large buzz around it, and I think everyone knows the hype curve. I think we're moving up now. They're starting to address some issues increasingly with I/O and cards, so it remains a problem. But the power in these cards is immense, and so it is important that we pay attention to that. So in previous versions, the GPU support was limited to the multifunctional direct solver, Solver 8. And what we found from our own testing and from feedback from the community is that you did need minimal input and output from the GPUs on these type of problems. And you really needed to make sure that you had massively parallel computations within the GPU core. So taking that all into consideration and the feedback we've gotten, we decided we would evaluate the performance under GPU for larger models using an iterative solver. And spoiler, we do see some significant improvement, and so that is what we have actually added. We've added the iterative sparse solver, now supports GPU calculations. I apologize, I don't have a picture of the menu here, but you do now have in the iterative sparse solver an option to turn on GPU calculations. And you can see here some of the behavior we got. Some of the models I can share, some I can't. Again, because of the proprietary nature, customer-provided models. But here are two of the models. And you can see we get the matrix solution speed up is great. It doesn't directly turn into all into wall time speed up compared to a single CPU because there are I/O issues or other things associated with the card. But we're paying very close attention to what's happening in hardware. And I wouldn't be surprised in 3 or 4 years from now, a lot of those issues go away, considering the advances and the changes they're making, including GPUs on cores, on actual CPUs. So this is the current wall time speed up that we're getting. In many cases, it's incredibly significant. So definitely give this a look if you don't have the GPU capability. It's a good time to maybe evaluate both it in the iterative sparse solvers on your type of problems. Analysis statistics reporting. So this is actually has some overlap with the next section when we're talking about the simulation environment, but I feel it has implications kind of on both the analysis runtime and on the GUI. So we do have this existing box. Hopefully everyone is aware of it. I know that anytime I run a job, I'm staring at this expectantly and to see the progress of what's going on. I think there's a lot of great information in here. And there's additional information that we can start adding. And so we took a look at it and decided for this first kind of evaluation, looking at what we could add to this job submission, was add 2 types of data that anytime people go to and look into our text files to find information on. The first is the iterative penetration check. This is what scales the iterative displacement vector, introduces extra Rassmann iterations. Yeah, as this starts from a small value and goes to 1, how fast it's going gives you an idea of how the simulation is solving, how much difficulty it's having. So this is a really important parameter in many cases. And then the number of warning messages is important. Now, I know we've all been accustomed, because some of these warnings to us have become common in some of the analysis, and we feel as an end user in many cases, okay, I know I have warnings, but you really don't know how many you're getting unless you're doing the searching and looking at that, and not everyone really looks at that anymore. So this puts it up front and center. Definitely your first run, if you have warning messages, you really owe it to yourself to go check those warning messages to make sure it's not indicating a problem. This is also useful, I think, when you're then reiterating and running that model over again. If you suddenly were running 4 warning messages, you can be pretty confident that it's probably the same 4 warning messages. But if you suddenly run your analysis and it says 5 and you had 4, you definitely need to go back and re-review everything. So this just provides that information for you more upfront, something we want to do more of elsewhere. That leads into the smarter simulation environment. A lot of the enhancements that we have done, and we're going to start off with a quite big one, quite a big project. So in previous releases of Mentat, there was no distinction made for the dimensionality of the model. That means that if I was to, in this case shown here, if I was to define a boundary condition, I saw all 6 degrees of freedom, even if I was doing an axisymmetric or planar type problem, right? And once you're accustomed to this, it's a bit of a pain, but it's not impossible to work around. For our newer users, it's a little bit of a disconnect as well, because they want to run a 2D model and they're suddenly be asking, maybe erroneously interpret it as saying, oh, I need to define my displacement in Z, where it just doesn't apply. So we've now added the model dimensionality. You can set it up here in the top menu, or you'll see it here with the model, and you can also change the dimensionality here. This allows you to prescribe whether you're running a 3D axisymmetric or planar model. And the great thing about this now is that all of that propagates through different menus. So now they're context sensitive, which is a favorite word of mine in this release, if you've been paying attention, in terms of the dimension chosen. So if I'm running a 2D, if I've essentially said it's planar, I'm now going to only see the degrees of freedom that apply to that versus 3D, where I will see all 6 degrees of freedom. This is only one example. I'll show some examples on the other page. If you use switches between dimensions, this was actually nice, is that the menus will change and the data will move to the appropriate value. So if I am running 2D and then I say, okay, I need to run it 3D, it will update appropriately when I make that change. Other examples we have, this is not really directly tied to the dimensionality of the model, but it has to do with dimensionality in general and degrees of freedom. And this is bolt control nodes, right? Many times you set them and you have to assign a boundary condition, again, using the 6 degrees of freedom menu. We've kind of just eliminated it entirely. We know the degree of freedom that's associated with that bolt control node. And so you only have to set the magnitude. You don't have to worry about the actual degree of freedom. We take care of that internally. Geometric contact, there's implications elsewhere. If I'm running 2D, I have curves, and I have 3D, I have surfaces, and we made sure this is consistent throughout. excuse me. Orthotropic and anisotropic material properties also have a change where we gray out things that don't apply. And then serial links is yet another example of where we do this kind of adjustment. So 106 menus were adjusted in the end. This was an incredible amount of work that was done by the team. And it really, again, this context-sensitive nature of the tool really improves the usability, we feel, of the product. If you see something that we happen to miss, please let us know. But we really worked hard on this, and I think it's a good start. More to come in future releases around that. Tables, I love. I think, like maybe a lot of analysts, there's a love-hate relationship with tables. Tables are extremely powerful, but manipulating them and defining them can be quite a tedious activity, particularly if you're going to subdivide segments and reduce data points. The first thing we added to this is that if I'm going to do this operation, maybe I want to operate on a new table because I don't want to accidentally lose my previous table. So now you can check Marc and say, I'm going to make these changes, but I want a new table created from it, right? I think that's a very important capability because it improves the robustness of working it. You don't have to worry necessarily then about deleting your table of record while you're trying to maybe simplify it. And the other thing we did is improve the option to remove a range of data points. Again, it makes it easier to work with a heavily populated table. Oh, I apologize for that. That is my plug came out. Okay. And so we have this new option to remove a range of data points. Predefined commonly used table shapes. So this is another thing that we think will make tables easier to use. It's not uncommon that people are doing linear ramps. There's a large number of different shapes that we know are common. We'd be interested to hear if there's certain other types of tables that use commonly that we can put in here just to make the definition much easier instead of having to enter data points yourself in a tedious way when you already know the shape of it and you just need to define the endpoints. So we now have these predefined commonly used table shapes that you can use and modify as you see fit. That gives you a bit of a head start when you're defining it. You can do time or normalized time. This one is also a really good implementation in the GUI, something that feedback is important on because we want to possibly see this more elsewhere. The default name of the table is automatically related to its shape. This is probably initially an overlooked by the casual observer of this capability, but it's actually very important because, again, it gives context to the shape of what you've created. And so now, if you were staying with default names, at least it doesn't say table 1. It actually tells you a little more about the table, just from the naming. And when you're using data points, also the extrapolation flag is switched off with these tables. Great. We're starting to get near the end, but still some really important and powerful small enhancements. During post-processing, we have a new option called skip the time that's been added. This skips to the increment with the time nearest to what time a user specifies. So here's an example I did where I have this small specimen that is being buckled and there's VCCT happening, and you can imagine my increment count gets very large. If I'm trying to see what's happening at a given time level, maybe to compare with the previous result, or maybe because that's a critical load in my mind, it's much easier to go back to that in the new version. In the previous version, I would come here and I would be scrolling and looking for that time. Now I can skip the time directly to 1.20 seconds. Definitely when you're trying to extract some data similar to maybe what you did in another analysis, at the same data point, it's also extremely useful. And especially in light of the stuff we've been talking about, tables, pass control we have on incrementation as well. Cutbacks, though, can really wreak havoc, as can automatic time stepping with increment numbers applying to a specific increment. So this makes that navigation and post-processing much easier. Rendering of solids. So before, this is how you would get the rendering of the solid. 2000, maybe around 2000, this was acceptable, but it is no longer really acceptable when you want to cut and paste and put something in a report or a presentation. So now you can get a much finer representation, CAD, just like you might in the CAD program. So we've now made that easier for when you go to do reports and presentations. You can get a much better looking solid body on your pair solid. So here we have a couple of my personal favorites just because of what they represent. It's not uncommon that you have a job and you want to create a copy of it. And this doesn't apply to just jobs. It's to everything we make a copy of. And I have maybe a very long name that means a lot to me, and I'm just indexing it slightly, or I'm changing a few parameters, and I make a copy of it. And when I do prior, I get job 2, right? So the whole name that I had defined previously is unavailable. I have to open it up, copy paste, or retype it. Hope I don't make a mistake. And so what we've done in March 2020 is now when you copy it, we do it the way people expect now. We actually take the name of the previous copy and then we index it. So now if you, maybe the index is all you want, or maybe you want to make a few additions, it's much easier because you just have to make a few edits versus retyping the whole thing. So that's prevalent across all copies in this March 2020 release for Mentat. And then this one is also one that I've struggled with for some time across, I think, a large part of the whole CA industry. It's not uncommon that when you create a structural analysis, even in a nonlinear tool, the default is small strain. So prior to March 2020, that was the default. In March 2020, we've now made large strain the default. We feel, I think correctly so, that the vast majority of our users turn on large strain. So just no longer making this change necessary when we multiply it by the number of users, the number of models they created, and the number of times they have to do it, it's quite significant. So large strain is now the default. We also took a look at this menu and said, hey, this is a pretty important functionality or a parameter that people set. So we put it more front and center in this case. So we changed the location so that it's up front on the job properties. It's much easier to see whether you've set it. And that also goes for the inverse now, is that if you need to run small strain for a reason, it's much more straightforward and easy to change it than having to go down one more level in the menus. So like I said, this is a favorite of mine because for anyone using tools for the first time, this is a very common mistake made, is to not do this. And in a nonlinear tool today, it should be the default. Just a few more enhancements before we wrap up. We're just about ready to wrap up. We have some miscellaneous things we did. If you remember, we did this with the menus in the past, and we wanted potentially do this more and more, where we had our solvers and we kind of categorized them. We do a clear distinction between 3D solid sheets and wire bodies by organizing this way, and I think it's a really positive thing we're doing that we could propagate elsewhere. If we get good feedback on it. I think just from a design point of view, it makes sense that we try and do this whenever we have large lists of entities. And then a quad sheet body can now be defined in the global 3D space instead of the local XY plane. So hopefully you saw some enhancements that speak to you. I think with the smarter solve and the smarter simulation environment, I think you have. That is part of our goal, is to provide something for everyone in every release. But also we have some really exciting things we've made to specific workflows. And again, I thank you for attending. I thank you to our teams at MSC who brought this all together. And we're very excited to have you use it and download it. And please provide us any feedback. And I think with that, Bhumi, we're probably ready for questions.
Thank you, Matt. Thank you for the wonderful presentation. Thank you, everybody, for sticking in throughout the presentation. We're really excited, as you can see. We do have some questions in the Q&A panel that have been sent out during the presentation itself. If you have any questions, you can type them now as well if you like. I'll read the question out loud, and then one of us will respond to you to those questions. So the first question is, fatigue life calculation is only available for elastomers?
Currently, yes. It's an elastomer capability in this release.
That's right. Okay. And then the next question is, can skip to time option be used to skip between the last increments of consecutive subcases automatically?
I'm trying to. Can you repeat the question? Just make sure I get it right. And Audrey, I don't know if you have a thought on this.
Yeah. So basically, the skip to time option can that be used to skip between the last increment of consecutive subcases automatically?
Yes, it should have a time. So if you're jumping between 1 second, 2 seconds, 3 seconds, etc. If I'm interpreting the question right, you should be able to do that. Yeah.
Okay. The next question is it possible to export a model with its boundary condition, load cases, and sets built in Marc to Nastran?
That's an interesting use case. So we have not looked at going from Marc to Nastran. Audrey, do you have any comments on that, or Joshua?
Yeah, I would say if you have, say, the model as a Marc data file, you can, say, always import it in Mentat. That gives close to 100% support, and then do the export from within Mentat to Nastran. I won't say it's 100% supported, but we try to make it more complete every release. So that would be, in my opinion, the recommended way to go.
Yeah, it'd be great. Whoever asked that question, if you want to reach out to me afterwards, I'd be happy to discuss it and understand a little more about the use case.
Yeah. Okay. The next question is, will no solid modeling options still be required to work with .mod files without pulling a Parasolid license?
Okay. Yeah, I think so.
If say the Parasolid data is there and you don't operate as such on it, it's not really required, and we can put it, say, in sort of quarantine and remain it like that. Whenever you wanna operate on it, it becomes a different story, of course.
Okay. The next question is, how do you expect making available fatigue life calculations for other kind of materials?
Yeah, so at this point, I'll say definitely elastomer was a focus, but you can look at what we've done at MSC as a company in terms of fatigue, and we're hoping to of course, expand this capability beyond elastomers, but I can't say right now what specific plans we have. We are discussing it internally, so we'll have more soon.
Yeah, please stay tuned, right?
Yes, exactly. In the meantime,
I was just going to say,
in the meantime, these, please, even if it's for another material, you can at least look at that capability. If you are interested in something like metals or different material types, please contact us to express your interest in that and what type and what some of your requirements might be, because if as we're thinking where we're going next, having that upfront and earlier will really help us.
Yeah, and really, we really like the enthusiasm here. The next question is, how does the new Coil option work in 2020 version, and how is it different from 2019 FP1?
So the new Coil, when you're working in 3D, doesn't have to be a revolution. And it's actually implemented much easier. It's a fairly easy implementation. You just have to, bring in your solid representation of the coil, mesh it, and then assign the beginning and end terminals. It is yeah. Audrey, did you have anything you wanted to say about it?
Yeah, maybe I can say that in 2019, the computation of the induced currents was based on an iterative process internally. Even if the material behavior itself is linear, it required a number of iterations, and even more if the material behavior is nonlinear. In 2020, when using this arbitrary shape setup, then those iterations are no longer required. And that basically explains why in 2020, this example which Matthew showed did require less iterations than the same solution for the 2019. So it's really a different algorithm to compute the induced currents.
Yeah. The next question is creating models automatically for Marc 2019, will there be a need to adapt the program for new input file adapted to 2020? Or will it be capable of readapting it?
They're talking about bringing in an older version and running it in the new version.
Let me see. I suppose. Yeah. So they're saying like, I think they have some sort of a way to create file automatically for Marc 2019 version right now, and yeah.
Yeah. Audrey, do you want to talk about any changes we made?
Yeah, let's say if you have your complete setup of the model in terms of say a Mentat database, so an MUD file, yeah, okay, then it's a given. We can open it up in 2020 and spawn the analysis. Then the model is basically given. If you build it up using a procedure file, then you can set say the version of Mentat being used to create that procedure file, say it was 2019. If you remove that and you base it on the default version, then say appropriate default settings based on 2020 will be applied. So it really depends a little bit on how you set up the model. If it's truly an import of an existing one or a recreation of it based on a procedure file, so or the session file.
Yeah. Maybe they can reach out to us or technical support if they get stuck in the process somewhere.
Sure.
Yeah. Okay, if you have any other questions, please type them in the Q&A panel. Okay, it looks like we do not have any new questions coming in. So with this, but if anybody has any question later in the day or any time, just feel free to reach out to us or to the technical support team. Thank you, everybody, for your time today. Thank you, Matt, for your wonderful presentation. Thank you, Audrey, for being the panelist, and Yashwant as well. And have a wonderful day, everybody.